want to give you a personal, somewhat historical and reflective survey on macromolecular structure determined by transmission electron microscopy, TEM. There can be little doubt that over the years, negative staining has provided electron microscopists with an enormous amount of information on protein, viral, and membrane structure. In general, data from negative staining has integrated very well with that derived from thin sectioning, metal shadowing, and freeze fracture. Negative staining has also given us a sound base from which the current advances in cryo-electron microscopy of frozen, hydrated, unstained material can be assessed. The higher resolution studies of Nigel Unwin, Richard Henderson, Hua Chu, Bob Glaser, and many others have mostly progressed from the somewhat lower resolution, negatively stained images of protein crystals, purple membrane, gap junctions, and the acetylcholine receptor, to give a few examples. It's exactly 30 years since the introduction of a standardized procedure for negative staining of viruses. This came from Sidney Brenner and Bob Horn in 1959. This technique, with a number of variations, has been widely applied to lipid suspensions, membrane systems, ribosomes, a large number of enzymes, and other fibrous and globular proteins. The principle of negative staining is really very simple. First, an aqueous solution of a heavy metal salt surrounds and penetrates the protein, ideally without interacting with the protein by binding to it or producing subunit dissociation. Then, the salt has to dry as an electron-opaque, amorphous glass around the protein and in the water-filled spaces between its subunits. This method for providing contrast within electron microscopical specimens was discussed initially by Hall in 1955 and Huxley in 1956. But really the concept is much older and was used by the early light microscopists. I want now to give you a visual demonstration of negative staining using the overhead projector. Situation in which I place some pieces of clear glass in a container and surround them by colored solutions. To start with, the glass is invisible, but once the stain is added, the varying shapes of the pieces of glass are clearly revealed. Because of the problems of bringing to the US dye solutions and pieces of glass, I've simply produced some reverse contrast images from a black and white diagram of viruses and proteins. I've used different colors to represent the different negative stains. For instance, the negative stains do not interact with our hypothetical biological samples. Here in our model, we have the hypothetical samples of biological material surrounded by a green stain. It could just as well be a different hypothetical negative stain. Again, not interacting with our biological material, surrounding, penetrating, and revealing. We have several negative stains, so in our model we can again use a different color to represent the surrounding contrasting material. And as a final example, a blue negative stain shows essentially the same thing. At the top we have biological material supported on a carbon film and surrounded by negative stain. The image that we see in the electron microscope is produced by the penetration of the electron beam through the biological material and the scattering of the electrons by the surrounding negative stain. Such images also occur in nature, for example, in calcified fossils. The next slide is of crinoids, or sea lilies. These are primitive segmented echinoderms. Note the scale marker here. The calcified animal is embedded in the darker stone, showing the segments very clearly revealed. The main negative staining salts used by transmission electron microscopists are listed on the next slide. In most cases, these stains are used as 2% solutions at neutral pH. Uranyl acetate cannot be neutralized and has to be used as a slightly acidic solution. The ammonium uranyl oxalate complex can be neutralized, but it is very photolabile and needs to be used when freshly made. Uranyl acetate also has a tendency to bind to negatively charged proteins and lipid phosphate groups. Indeed, in some cases, uranyl acetate produces gross and unacceptable protein aggregation. Uranyl acetate does, however, impart a superior contrast when compared to the other stains. But it has always been my opinion that one should try to use a range of different stains to image any one protein, since slightly different molecular features may well be revealed. Huxley and Zubai in 1960 were probably the first to study ribosome particles by negative staining. During the early and mid-1960s, several investigators started to use the technique to study protein molecules. I will mention a few of the early workers, such as Fernande Moran in the US, Ernie van Bruggen in the Netherlands, Robin Valentine and Nick Wrigley in the UK, Levin in Sweden, and Kiselev in the USSR. Others, such as Thomas Anderson, Bob Horn, and Aaron Klug, concentrated on the study of virus particles. In general, since these early studies, an increasing number of biochemists, cell biologists, and microbiologists have started to use negative staining for isolated and purified enzymes and proteins of high molecular weight. By that I mean molecular weight in excess of approximately 150,000 Daltons. These studies have been performed on single dispersed molecules, thin crystals, and two-dimensional crystalline arrays. That is, monomolecular arrays. Many negative staining studies have also been performed on membrane systems obtained by subcellular fractionation techniques and on liposome suspensions. Even though negative staining has its limitations, there can be little doubt that of all the available EM specimen preparation techniques, it has over the years made available the greatest amount of medium to high resolution data. That is in the range 1.5 nanometers to 2 nanometers. We are all, of course, well aware of the contributions that have been made by the freeze fracture technique and recently of the exciting impact of cryo-electron microscopy of unstained frozen hydrated material. But I will not be considering these approaches further in this tutorial lecture. The highest resolution studies have been performed on thin crystals negatively stained with glucose or ice embedded, such as of crotoxin, such as of the crotoxin complex by Hua Chu and his colleagues, and bovine liver catalase, and the two-dimensional membrane crystals of bacteria rhodopsin in purple membrane by Nigel Unwin and Richard Henderson. These studies are now approaching 0.4 nanometers. Also, bacterial surface layer glycoproteins have been studied by Wolfgang Baumeister and his colleagues in Munich and Sven Hovmola in Stockholm. With single, randomly dispersed molecules, it has not yet been possible to achieve the same resolution, although tremendous advances have been made by Joachim Frank, Martin van Heel, and others using multivariate analysis. The production of two-dimensional monomolecular layers is considered by many to be the most satisfactory line of investigation, as the average molecular information available in the optical and digital Fourier transform can fairly readily lead to 2- and 3-dimensional reconstructed images. Before going on to discuss the imaging and analysis of some of the protein molecules and enzymes that I have dealt with myself over the past 20 years or so, I want to spend some time discussing 2 of the variations that have been developed for producing negatively stained specimens. The simplest approach is usually termed the single droplet technique. I still make use of this very reliable procedure shown to me by Dr. Benedetti in the Netherlands in 1965 when I started my PhD. This technique is depicted in the next slide. This technique, the protein sample is positioned on a clean parafilm surface and is picked up by a carbon-coated EM grid. The excess fluid is then removed by touching a filter paper onto the edge of the grid. The second stage is when a droplet of the stain is picked up on the same grid and allowed to disperse around the protein layer. Again, the excess fluid is removed by touching the filter paper onto the edge of the grid, and finally it is necessary to put the filter paper between the tips of the forceps. The grid is then positioned onto a Petri dish, onto a filter paper. This technique works well for protein suspensions, isolated cellular membranes, liposomes, lipid micelles, and viral particles. If spreading problems are encountered, it is useful to include the peptide antibiotic bacitracin. Similar results can be obtained by spraying a mixture of negative stain and biological material onto the carbon-coated grid, but this approach is usually unnecessary. The next slide lists a number of negative staining variations. These different conditions can prevail during the negative staining process. Any of these conditions may induce desirable or undesirable molecular distortions or staining features. For instance, if there is a film of negative stain alone with the protein molecules embedded in it, or an extremely thin carbon film, there may well be mobility of the substrate in the electron beam, giving molecular distortion. Usually, this situation might be thought to bring about a superior signal-to-noise ratio, as shown in the next slide. The thinner the carbon film, the more desirable the imaging. The thicker the carbon film, the greater the noise in the image. If there is a double layer of carbon with molecules and stain sandwiched between the carbon films, there may be even negative staining, but at the same time a greater amount of molecular compression. This is depicted diagrammatically on the next slide. Here we have a biological particle, a protein. Example B, the protein is supported on the carbon film, producing some distortion and some slight flattening of the protein molecule by the surface tension of the surrounding stain. Example C, a double layer of carbon with a thin layer of stain trapped between the carbon films and around the protein molecule. There may well be an even greater amount of molecular compression and protein distortion. The next slide shows diagrammatically a varying depth of negative stain from left to right. At the left-hand side of our diagram, the surface tension forces during the drying may well produce molecules which are orientated all in one particular dimension. In the deeper stain, the molecules have a greater mobility. They can be more randomly orientated in a rather thick layer of negative stain as it dries. actual negative staining procedure was developed in 1974 by Ivone Pasquale Ronchetti and Bob Horn. They termed this procedure the negative staining carbon film procedure. These workers applied the technique primarily to icosahedral viruses and to a more limited extent to filamentous and rod-like viruses. The distinct advantage of this procedure is that it produces the formation of regular, two-dimensional, paracrystalline viral arrays. These arrays are suitable for optical diffractometry and digital image analysis. Can also be readily applied to purified macromolecules. But relatively few people have pursued this approach, despite its simplicity and the considerable potential that it holds. The next slide shows diagrammatically the various stages of the negative staining carbon film procedure. Protein or enzyme solution at a concentration of approximately 1 milligram per ml, and ideally in a low ionic strength buffer, is mixed with an equal volume of 2% ammonium molybdate, usually at pH 7.0. This solution is spread evenly on the clean hydrophilic surface of small pieces of freshly cleaved mica. The excess fluid is drained off onto a filter paper, and the remaining fluid is allowed to dry at room temperature. The speed of drying can be slowed by placing the mica over a moist filter paper in a Petri dish. Drying at 4 degrees is not of any benefit. Indeed, conventional crystallization of proteins is usually better at room temperature. A fairly recent, important innovation, due to Goretti Magaldi and colleagues, potentiates the formation of two-dimensional crystals. This is the inclusion of 0.1% polyethylene glycol of molecular weight 10,000 in the ammonium molybdate solution. After drying, the strips of mica are coated with a thin layer of carbon, and the corners of the mica are then marked with a water-insoluble black fiber tip pen. The thin film of carbon, together with adsorbed single protein molecules and two-dimensional crystals, is then floated off on the surface of 2% uranyl acetate. The thin carbon film is almost invisible, but is revealed by the black pen marks. Portions of the floating film are then picked up from beneath the stained surface using wholly or perforated carbon films or simply 400 mesh grids. The excess uranyl acetate is then removed using filter papers, as in the single droplet procedure. The actual handling of the mica strips throughout this procedure is very easy, and each strip may provide up to 8 or 10 EM grids for study, depending on the size of the mica strip used in the first place. The next slide lists some of the proteins with which I've had some success using the negative staining carbon film procedure. My earliest work was done with the aproferritin molecule and the Bordetella pertussis 22S antigen. At this stage, in my earlier studies, I was not using the inclusion of polyethylene glycol. More recently, all my work has been done using this additive and has produced considerable success with alpha-manosidase, catalase, and tripeptidyl peptidase 2. And I will be giving you some examples of these proteins. There are some applications of negative staining using both the single droplet and the negative staining carbon film procedure. Most of the examples I will take from my own studies, but I could equally well have borrowed examples from numerous other investigators. I think it's best to start at the beginning. For me, the beginning was in 1965, when I joined Dr. Geoffrey Haggis in Edinburgh and started work on the TEM of erythrocyte membranes and liposomes. Within a year or so, I had discovered 2 proteins associated with the erythrocyte membrane. I termed these proteins taurine, or single ring protein, and cylindrin, or cylindrical protein complex. We now know that cylindrin is a multi-catalytic protease complex, which is present in many tissues. It has at least 5 subunits and a molecular weight of about 800,000 Daltons. It has dimensions of 11 times 17 nanometers. The function of taurine is still unknown. It has a single subunit of molecular weight 20,000 and a native molecular weight of 200,000. This indicates to us immediately that there are likely to be 10 subunits in the taurine ring. Taurine has an external diameter of 12 nanometers and is remarkably similar to a bacteriophage protein termed P22F. Starting with taurine. In the next slide, we have a model of the taurine molecule. To assist your understanding of the structure of a ring-like protein, we have here 2 models made from plastic beads. The plastic models are lying flat on a surface and have been photographed directly from above. Next slide, please. Moving now to a negatively stained image of the protein taurine. In this case, the negative stain is sodium phosphotungstate spread by the single droplet procedure. We have an array of molecules in a very thin layer of negative stain, and the ring-like images show up fairly faintly in this shallow negative stain. In the next slide, we have the same material revealed by uranyl acetate staining. Actually, this is produced by the negative staining carbon film procedure. The procedure has not, in this instance, produced a 2-dimensional array. There is some clustering of the taurine molecules, some aggregation. The black arrowheads indicate little doublet molecules, and I'm putting it to you that these represent molecules that are standing on their edge, supported by the negative stain. Next slide, please. The concept that I gave you a few moments ago, that the taurine ring might contain 10 subunits, is supported by the Markham rotation technique for photographic enhancement. Here and here we have an indication of 10-fold symmetry. When the image is rotated 9 and 11-fold, there is not an equivalent enhancement. Next slide, please. In shallow negative stain, the taurine molecule will always tend to lie on its side. One can imagine a handful of coins thrown onto a table. They nearly always fall flat. But in negative stain, one might occasionally get the molecules supported on their edges. And this is shown in the next slide. The model here shows different depths of stain supporting our taurine molecule. The proposition is that a ring-like molecule can actually give a little doublet electron-optical image. And in the next slide, negatively stained with sodium phosphotungstate, this is what we have. Indeed, in the deep negative stain shown here, the molecules will be orientated at several different angles relative to the electron beam, exactly as in the earlier slide where I represented an increasing depth of negative stain. The predominant image is a little doublet, and this is produced by the vertically orientated taurine molecule. Next slide, please. The reason for this doublet image is derived directly from our molecular model. the thickness of protein in a vertical direction represents a peak of electron transmission. The summated thickness of protein across the molecule gives us this curve. Slightly different here because of the orientation of the bead-like molecule. But in both cases, a peak, two peaks of electron transmission, which in the electron optical image give us a doublet. Some electron microscopical images of the enzyme alpha-manosidase from jack bean. This enzyme gives a double dot image in sodium phosphotungstate. This is because alpha-manosidase is a dimeric protein, not a ring of subunits. The biochemical support for the purity of this enzyme and knowledge of its subunit composition is very important when interpreting the EM images, and really this applies to all purified proteins. At a slightly higher magnification, I think you see the double dot images with greater clarity. Randomly dispersed in this pool of sodium phosphotungstate. In this case, by the single droplet technique. When spread on mica by the negative staining carbon film technique, alpha-manosidase tends to form tube-like arrays. In this case, in the absence of polyethylene glycol, but when polyethylene glycol is included, the tube-like arrays tend to form parallel bundles. Unfortunately, arrays of this sort are not really suitable for doing digital image analysis. Turning now to the protein cylindrin, also termed the multi-catalytic protease complex. Here we have a model of the cylindrin molecule, orientated on end and on its side, giving you some indication of the subunit composition. The molecule has a reel-like composition, possibly with 8 subunits in the outer ring, and indicated here, the thinning with possibly 6 or 7 units in the 2 central rings. This is certainly open to question at the moment. The cylindrin molecule negatively stained with uranyl acetate by the single droplet technique. Here we have the molecule orientated on end and on its side, randomly dispersed throughout the fairly evenly spread negative stain. Another slide of the cylindrin molecule, this time prepared by Robert Oliver in Austin, Texas. At the time Robert Oliver did this work, he thought that the molecule was an amino-acyl tRNA synthetase complex. More recent biochemical evidence disputes this. The stain in this case is methylamine tungstate. Here we have an example of mobility of the carbon support film. If you look closely at some of the cylindrin molecules, you'll see possible compression and extension of the molecule due to the mobility of this very thin carbon film within the electron beam. This is an example of the negative staining carbon film technique performed using cylindrin, but in the absence of polyethylene glycol. The molecules have clustered together in several places, but these clusters do not really show any degree of regularity. Indeed, the black arrowheads indicate groups of 4 molecules which are coming together in a regular manner, but in a manner that really prevents a further build-up of a 2-dimensional crystalline array. These molecules are offset end to side, end to side, end to side, as groups of 4. Sometimes the molecules do cluster on end, as in the center of this slide. Unfortunately, I haven't detected large regions of this type, this end-on packing, which would almost certainly produce a hexagonal array. The possibility is that using different staining conditions, perhaps increasing the pH of the ammonium molybdate solution, would increase the tendency for the molecules to stack themselves in this type of orientation. The evidence for eightfold rotational symmetry comes from the Markham rotation technique. In this case, eightfold enhancement of the original molecule, original unrotated molecules, 7, 8, 9-fold rotation, with the most predominant enhancement coming at eightfold rotational symmetry. This is open to question. Work from the laboratory of Wolfgang Baumeister indicates 6 or possibly 7-fold rotational symmetry, but we have here a very complex molecule, as indicated by the model. It is my belief that in all probability the central rings do not have the same symmetry as the outer rings of the stacked subunit composition. Now, when we include polyethylene glycol in the negative staining carbon film technique, the molecule cylindrine has a much greater tendency to form ordered arrays. In this case, we have linear arrays of the molecule, not unlike the alpha monosidase. This really is an example of an early stage of the crystallization process. Undoubtedly, this occurs during the drying of the protein in the presence of molybdate and polyethylene glycol onto this hydrophilic mica surface. An example of a more regular crystalline array, molecules end to end, producing parallel rows of molecules. Areas such as this are almost suitable for digital image analysis. And at a slightly higher magnification, the same sort of thing. Here we have a row of molecules with discontinuities, and there a couple of molecules which are orientated at 90 degrees to most of the others, obviously interfering with the regularity of the packing. Here we have an example produced by Andreas Holzenberg from the digital image analysis that he has done so far. The end-to-end image of the stacked row of molecules. Note here that the linearity is slightly offset from molecule to molecule. And I think this does, in fact, come out in the electron-optical images. For instance, the side-by-side stacking of these molecules does seem to tend to be offset. Perhaps one would expect this from a real-like composition rather than a smooth-surfaced cylindrical composition, i.e., that alignment is somewhat less likely than the offset alignment that we have here. I have detected this very parallel alignment of the molecules, but it does seem that they tend to slip down adjacent to one another. For my final example of negative staining, I'm going to talk about my current work on the enzyme catalase, isolated from human erythrocytes. This is an enzyme of 250,000 molecular weight. It contains 4 identical subunits. Now, compared with bovine liver catalase, on which there's been a great deal of work performed on the thin crystalline sheets, there is very little EM work on the human erythrocyte enzyme. This enzyme does not tend to form thin crystalline sheets in the conventional crystallization process. Tube-like arrays have been reported by Kiselev and his colleagues in the early 1960s. I have been trying to use the negative staining carbon film procedure to produce 2-dimensional crystals from human erythrocyte catalase, and have had some limited success so far, but success only when polyethylene glycol is included. This work has been performed in collaboration with Andreas Holzenberg, who undertook the digital image analysis. Here we have an example of a 2-dimensional crystal of human erythrocyte catalase. Discontinuities in the crystalline sheets, a gap here, and to the right-hand side, a multi-layer crystal. Undoubtedly 2 layers of molecules in this region, a single layer of molecules, and background carbon film. The same sort of thing, but showing a larger regular crystal. Single molecules, unfortunately, lying on top of the crystal in this instance. Areas such as this in the center might be suitable for digital image analysis, but one certainly would not use regions where single molecules are overlapping the crystalline array. The same sort of thing, crystalline sheet, free molecules in this region here, and double or multi-layer crystals in this right-hand corner. Regions such as this might be suitable for digital image analysis, but obviously not with a discontinuity running down the center. This is a lower magnification field, giving an example of the sort of region that we've used for the digital image analysis. A large region of great regularity of a two-dimensional crystal of human erythrocyte catalase selected by Anders Holzenberg for the digital image analysis. The numerical transform is given here. The resolution shown in this numerical transform is 2.1 nanometers. The optical transform, obtained from a slightly larger area of crystallinity, diffracts out to 1.4 nanometers. An example of the index diffraction pattern is given here. The Fourier peak filtered image of the original area selected is shown in this slide. Comparison of individual molecules shows that there is very little difference in the apparent subunit structure within these individual molecules. This gives support for the true crystallinity of the original area selected for diffraction. Here we have an example of the magnified filtered image of a single human erythrocyte catalase molecule. The contours reveal clearly two of the four subunits more clearly than the other two. And the region taken from the second encircled region of the filtered image, again showing two of the four subunits more predominantly than the ones at the side. This is undoubtedly due to the discrete orientation of the molecule within the two-dimensional crystal. The very recent work that I've been doing indicates that human erythrocyte catalase has a tendency to form a second and possibly even a third crystalline state. And here we have small patches of crystallinity within which the molecule is certainly orientated somewhat differently, probably on edge, compared to the previous two-dimensional crystals that we have analyzed so far. And in my final slide, the possibility of a third crystalline state. Unfortunately, the regions are not sufficiently regular to perform digital image analysis. If the work at the moment, future investigations may well enable me to produce greater regions of regularity in this particular crystalline state. The advantages to be gained from 2 or 3 different crystalline states relate very much to the reconstruction of 3-dimensional images of the protein molecule rather than 2-dimensional images, reconstructed images of the type I've just shown you. Of the work I've presented, indeed I hope that the 2 negative staining techniques and the data that I've given you speak for themselves. Instead of a summary, I'm going to leave you with a quotation, or with what might well be a quotation, from the late and great Richard Feynman, a physicist who had an insatiable curiosity for all things scientific. These words might well have been said by Richard Feynman. Indeed, in the videos that I've seen of him, discussing his life and his work and his scientific activities, he repeatedly came up with the phrase, "It is all very interesting." For me, molecular imaging by TEM is very interesting. Indeed, I hope that it interests you as well.